Hi everyone, it's Mr. Bowman, and I am going to show you how to use the calculator to solve problems with parametrics in this video. So we're going to start out with a superhero example. In this scenario, Lois is driving away from Metropolis at an average of 65 miles per hour in order to cover a story. 3 hours after she leaves, Superman finds out that there is a bomb in her car. Oh no. That is set to go off in 2 hours and leaves immediately. Superman flies leisurely at 155 miles per hour. We're going to fill in the chart below with the distances that Superman and Lois are from Metropolis at the end of each hour. So Lois, who is driving a constant 65 miles per hour, is 65 miles from Metropolis after 1 hour. She is 130 miles after 2 hours, 195 miles after 3 hours, 260 miles after 4 hours, 325 miles after 5 hours, and 390 miles after 6 hours. Superman does not find out for 2 hours that there's a bomb on board Lois's car. So for the first 2 hours, he's just sitting there in Metropolis. Actually, for the first 3 hours. He then finds out 2 hours from then the bomb is going to go off. So he takes off at 155 miles per hour. So at the end of hour 4, he is 155 miles away from Metropolis. And at the end of hour 5, when the bomb is set to go off, he is 310 miles away from Metropolis. Bomb goes off. Boom. Unfortunately, Superman was not flying at his full capacity, so he did not quite make it to Lois in time to save her in this scenario. So, no, he does not save Lois in this scenario. How fast would he have to fly to save Lois at the last moment? Well, he would have to fly 325 miles over a 2-hour period, and that would be 162.5 miles per hour. So what we want to do is we want to model this situation using parametric equations, because Lois's position, think of it in terms of x and y coordinates, and Superman's position in terms of x and y coordinates are functions of a third variable, time. So Lois is moving horizontally, and her distance from Metropolis, call it x, is going to be her velocity times time, so 65t. Lois, let's assume she's traveling on flat ground, so her height, her vertical distance above the ground, is a constant, so we just want to put some number in there, so we'll put Lois's height. We'll say that she's 6 feet tall. Superman, on the other hand, is flying at 155 miles per hour, but he does not start until the end of the 3rd hour. So we're going to take his velocity, 155, times time, but we want to do t minus 3 because at time 3 is when he actually starts. Okay? How about his height? Well, we could pick any constant. We're going to pick 100. We'll assume he's 100 feet above ground. And then the finish line parametric equations, we're going to leave this the way it is for now. What we're going to do now is we're going to transition to the calculator, and we're going to talk about how to set up the calculator and the window in the calculator so we can see this scenario play out. The first thing I want to do is I want to grab my calculator and I want to put it in parametric mode. And to do that, we go over to the mode button and we go down until we find the row that has this information: function, parametric, polar, and sequential. And we switch to parametric, and then we go back to y equal. And you're going to see something here that looks different from normal function notation. You're going to have an equation for x, you're going to have an equation for y, and there's going to be this subscript t. So for x1 and y1, we are going to put in the equation for Lois. So if you remember, Lois's horizontal position was her velocity times time. And how do you get t? If you hit the xt theta n key, t will pop in there. And our calculator uses a capital T instead of a lowercase t for that. Since Lois's vertical position is not changing, we put a constant in there, and we're going to say that's her height in feet. Superman, on the other hand, is flying at 155 miles per hour, and he does not start until after 3 hours. So we're going to put t minus 3 in here. And his vertical position, we're going to put 100 in for his height, or 100 feet. Now when you click on the window, you got a lot of other information here. First of all, you have to think about what t represents. And t represents time, but in hours. So in our table, we went from 0 to 6 hours. So we're going to do that, 0 to 6. T-step. How often do you want to plot points? And we plotted points every hour. We're going to start out with every hour, but we're going to change that. And then the window that you actually want to see. Well, if you think about it, we want x minimum to be at least 0. So we'll put 0 in there. X max in miles. If Superman flew for 6 hours, he would be about 500 miles from his starting point. X scale, how often do we want to put tick marks? We'll put tick marks every 100 miles. Y minimum, well, the ground would be 0, and Y maximum, it needs to be higher than Superman flies. So we've set Superman's height of flight at 100, so we'll set X max at 150. And then we're going to go ahead and graph this. Okay, now that graph happened way too fast for us. So the red line at the top is Superman's path, and the blue line at the bottom is Lois's. So what we're going to do a better job of simulating this is we're going to force the calculator to graph more points. And the way we're going to do that is we're going to make t-step very small, forcing it to graph more points. So we'll start out with something like 0.01. So basically every 1/100th of an hour, the calculator is going to plot a point for us. So let's graph that and see if that worked. And we saw another problem here. That problem is that it graphed Lois's path first and then Superman's, and not at the same time. So we've got to go back to mode, and we've got to change it to simultaneous down here. So we're going to select simultaneous, and then we're going to go back and graph one more time and watch this all unfold. So there's Lois. Here comes Superman. Almost caught her. He surpassed her at the end, but we know he didn't catch her in time. If we want to slow that down even more, we can make t-step even smaller. So instead of every 100th of a second, maybe we plot every 10,000th of a second. And now it's going to take the calculator longer to do this, and you can see that it's showing Lois's path there when she first starts, and eventually Superman's going to come along here. But this is really too slow and boring, so we're going to hit the window button again. We're going to quit. We're going to hit the window button again. We're going to try and quit. And we're going to hit the window button again, and we're going to set our step at 0.001 and then graph it one more time. And this is a much more reasonable time frame for us to wait to watch this all unfold. So there's Lois at 100 miles from Metropolis. There's Lois 200 miles from Metropolis. Here comes Superman there's Lois coming up on 300 miles from Metropolis, and Superman is catching up, but about there is where the bomb goes off, and Superman did not quite make it. However, if we speed him up just a little bit to 162.5 miles per hour, which obviously he could do, then he would catch Lois and save her. The next example we want to talk about is a situation where we're shooting or throwing something straight up into the air. And in this case, we're shooting a flare-up from a ship's bridge. So that's where the pilot actually drives the ship from. And it's 75 feet above water. It has an initial velocity of 76 feet per second. And this equation, some of you probably recognize from physics. It tells you the position, in this case, the height of the object with respect to time. There are three parts to this. The first part is due to gravity. The second part is due to how fast the object leaves where it's starting from, its initial velocity. And the third part is due to its initial height. So S is height in this case. T is time in seconds. V0 is initial velocity. And S0 is initial height. And for this particular equation, initial velocity would be in feet per second, and initial height would be in feet. Otherwise, we have to change that negative 16t squared out there in front. So if we want to write these using parametric equations, so we can talk about the position of the object with respect to time, well, x is just going to be a constant. Because if something is moving straight up and down, its x-coordinate is not changing. And y is going to be replaced by this equation, negative 16t squared plus v naught t plus s naught. Okay? And so what we're going to do is we are going to use our calculator to generate a table of values based on these parametric equations. So here we are back at the calculator. We're going to get rid of these Superman Lois Lane parametric equations, and we're going to put in an equation for this flare that was shot straight up. X is a constant. I'm going to pick something like 5. So it's basically, no matter what y is, the x coordinate is going to be 5. Y is the three-part equation, negative 16t squared, the part due to gravity, plus the initial velocity times time, which was 76 feet per second times time, plus the initial height, which was 75 feet above ground. And in this case, instead of making a graph of this, because the graph is going to be pretty boring, it's just going to go straight up and down, what we're going to do is we're going to make a table so we can see the height of the object with respect to time. So how do we do that? Hit second and the window button, and the table start is going to be where we start t at. So we're going to start t at 0, and we're going to make t go up in 1 second increments. So let's now hit second and the graph button to get our table, and you will see there we have it. So at time 0, the object starts at an x-coordinate of 5 and a y-coordinate of 75 because it started 75 feet above the ground. 1 second into its flight, the object is at 135 feet. 2 seconds into its flight, 163 feet. And as we all know, things that go up must come down. So now at 3 seconds, it's actually starting to fall. At 4 seconds, it's at 123 feet above ground. At 5 seconds, 55 feet. At 6 seconds, negative 45 feet above ground. That doesn't make sense. What that tells me is that the object struck the ground somewhere between 5 and 6 seconds. So if you want to get a better idea of when it actually struck the ground, what you can do is you can go back to the table set by hitting second and the window button and say, you know what, I'm going to start at 5 seconds, but I'm going to go up in tenth of a second increments because I know somewhere between 5 and 6 seconds is when the object hit the ground. So we go back to our table and we can see that the object struck the ground somewhere around 5.6 seconds. If you need to be more accurate, you can start at 5.5 seconds and go up by a smaller increment yet. So 5.5 and go up by 0.01, and we can really get an accurate idea of exactly when this thing struck the ground. So this thing struck the ground at approximately 5.59 seconds because its y coordinate went from positive to negative at that time. The next example we're going to do is called projectile motion. So something like throwing a baseball or kicking a ball, something that's not going straight up and down. So in this example, you can see this diagram of a baseball player, and the ball has an initial height, which we will call y0. It has an initial velocity, and we're going to represent that with the vector v, and it has an initial angle. We call that theta. So the path of the ball can be broken down into a horizontal and a vertical component, just like the velocity can. And the position of the ball can be found by taking velocity times time. The horizontal position, taking the horizontal velocity times time. The vertical, taking the vertical position times time. So how do we do that? Well, if you remember, the vector v would be represented by the magnitude of the vector v times the cosine of the angle. That would give us our horizontal component of velocity, and the magnitude of the vector v times the sine of the angle, and that would give us the vertical component of velocity, and that's the initial velocity. And then all we'd have to do is factor in initial height and gravity for the vertical, and then factor in time to figure out position. So x, the horizontal position of the ball, is going to be found by taking v0, the initial velocity, which is the magnitude of the velocity, times the cosine of the angle times time. We're not going to write them in exactly that order. We're going to write it in this order. So v0 times t times the cosine of the angle. And basically the first and the last part of that are the horizontal component of velocity. And then we multiply by time. The vertical is going to consist of three parts. Negative 16t squared, that's the part due to gravity, plus v0 times t times the vertical component of velocity. So v0 times sine theta is the vertical component of velocity times time plus the initial height y0. So we are going to take that information and we are going to apply it to this scenario below and see what happens with this baseball. So Brock hits a baseball 3 feet above the ground with an initial velocity of 150 feet per second at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot fence that is 400 feet away? Okay, so let's write the equations for the horizontal and vertical location or position of the ball at any given time, and then let's go solve this on a calculator. So x is equal to initial velocity 150 times t times the cosine of 18 degrees. Y, negative 16 t squared plus 150 times t times the sine of 18 degrees plus the initial height of 3. Now we're going to plug those into our calculators and make sure we're in degree mode as well as parametric mode so that we can figure out what happens and whether or not the ball is a home run by clearing a fence that is 20 feet tall, 400 feet away from home plate. So here are our two equations for the horizontal and vertical location of the ball with respect to time. The one thing that we haven't done yet is to make sure our calculator is in degree mode because the angle is in degrees. So we have to hit the mode button and go over here, and yep, my calculator happens to be in degrees. Okay, so now we'll go back to where we were at before, and we could graph this, but honestly this is an easier question to answer using a table. So what we're going to do is we're going to start the table at time 0 when Brock hits the ball, and we're going to look at it in 1 second increments to begin with. And we're going to watch and see where y goes from positive to negative, where the ball hits the ground first, and then we're going to zoom in on, so to speak, where it approximately was 400 feet away from home plate and see if it was tall enough, high enough to go over the fence. So somewhere between 2 and 3 seconds, the vertical switches from positive to negative, so we know the ball hits the ground. You'll also notice that somewhere between 2 and 3 seconds, the ball's horizontal is between 285 and about 427. So it's possible we have a home run here, but we need to take a closer look. So we're going to set our table up to start at 2 seconds and go up in 0.1 second increments. So second in the table. And now what we're looking for is when the ball is 400 feet away from home plate. Oh, we're really close there at 2.8 seconds. Is the ball high enough to go over the 20-foot fence? And the answer is no, because you can see the ball had already started coming down at that point. So again, we could get a more accurate answer if we started at 2.8 and went up by smaller increments, but we can see at about 400 feet, the ball is only about 7 feet off the ground. All right, so we're going to look at one more example like that. This time it's Jared, and he hits the ball with initial velocity of 160 feet per second, an angle of 20 degrees and 3.5 feet off the ground. Same fence, 20 feet high, 400 feet away. We're going to write the parametric equations. So 160 t times the cosine of 20 degrees, y negative 16 t squared plus 160 t times the sine of 20 degrees plus the initial height of 3.5. And we're going to go over, plug those into our calculator and see if Jared hits a home run. Okay, so that was a pretty easy change. We needed to change the initial velocity, the initial angle. We also needed to change the initial height in our equations. We're going to go over to our table. We're going to start at time 0, and we're going to go up by 1 second increments to start out with to figure out about when the ball hits the ground. So second in the table, and the ball hits the ground between 3 and 4 seconds. So we're going to go back. We're going to set the table up to start at 3 and go up by smaller increments than 1 second. 0.1 I think would be good to start out with. And let's see when the ball is 400 feet away. Well, turns out that after 3 seconds it's already past 400 feet. So we're going to go backward a little bit here. And we're going to go to between 2.6 and 2.7 seconds. The ball that Jared hit is going to reach the fence, and you can see that when it reaches the fence, it will be somewhere between about 34 to 35 feet and about 37 to 38 feet high. So Jared does actually hit a home run. You could ask other questions like, how far does the ball go before it hits the ground? Well, somewhere between 3.4 and 3.5 seconds. Y changes from positive to negative. So that Jared's home run ball hits the ground somewhere between 511 and 526 feet. If we wanted a more accurate answer, we could start at 3.4 seconds and go up in smaller increments. We can also do things like find approximately how high the ball went. Now, since it was in the air for about 3.5 seconds, we should be able to go back to about half of that and figure out the maximum height. So if we scroll back here to somewhere around 1.7 seconds, we see that we have a maximum height of about 50 feet. And you can see its maximum because at 1.6 seconds, the height is 50 feet. It's a little bit larger at 1.7 seconds. And then it's starting to get smaller again at 1.8 seconds. And the last example we're going to do is a circular motion example, a rider on a Ferris wheel. So Jane is riding a Ferris wheel with a radius of 30 feet. The wheel turns counterclockwise at a rate of 1 revolution every 10 seconds. Assume the lowest point is 6 o'clock of the Ferris wheel is 10 feet above ground. Jane starts her ride at the 3 o'clock position. Find parametric equations to model Jane's path and use them to find Jane's position 22 seconds into the ride. Okay, so I think this warrants a picture here. And we are going to use the x-axis as the ground, and the y-axis is going to serve as the center of the Ferris wheel. So we were told that the Ferris wheel, the bottom position is 10 feet off the ground. By the way, this is not drawn to scale. And the radius of the Ferris wheel is 30 feet. So the coordinates of the center of the Ferris wheel are going to be 0, 40 because we're on the y-axis and we're adding the 30 feet to the 10 feet. Radius is equal to 30 feet. The rider, Jane, starts at the 3 o'clock position and goes counterclockwise. Well, that's an angle of 0 degrees or 0 radians, and she makes 1 revolution every 10 seconds. So our x equation is going to be, or our x position, 30, the radius, times the cosine of the angle at any given time. Well, the easiest way to do this is in radians. You could do it in degrees as well if you want, but we know that Jane makes a full rotation, 2 pi, every 10 seconds, and then we're going to multiply that by t. So, for example, if t were 10, then we would be taking the cosine of 2 pi. If t were 5, then we would be taking the cosine of 2 pi over 5, or half a rotation. For y, we have to factor in the center of the Ferris wheel at 40 plus 30 times the sine of 2 pi over 10 times t. And we do have to make sure that we are in radian mode when we do this. If we were going to do this in degree mode, our equation would be slightly different. It would be 30 cosine of 360 degrees divided by 10 times t, and y would be equal to 40 plus 30 sine of 360 degrees divided by 10 times t, because Jane makes 1 complete rotation every 10 seconds. So we're going to do this in radian mode. All right, so here are our equations for Jane's position, horizontally x, vertically y, with respect to time. I need to go to my calculator mode and make sure that I put the calculator in radian mode because I wrote the equations using radian measures. And my window, I am going to graph from t equals 0 to t equal 20. So that's 2 complete revolutions. We'll do a small increment for time. X min and X max. This is going to be kind of interesting. You got to think about the picture that we looked at. So our Ferris wheel had a radius of 30. So and its center was on the y-axis. So I'm going to go from negative 40 to positive 40 for X. And we're going to go in increments of 10. And I'm going to go from 0 to the maximum height of the Ferris wheel would be 10 plus the diameter of 60, so that would be 70. So let's say we go up to 80 and we go in increments of 10 as well. And we're going to now graph Jane's position with respect to time. And you can see this tracing out Jane's position with respect to time. We want to speed this up a little bit, so I'm going to stop it. And I'm going to change my t-step to 0.01, so it should make it about 10 times faster. And we'll graph this. And there's the Ferris wheel. Now, you are probably looking at this saying, wait a minute, Ferris wheels are circular. And that's because our picture is distorted. So what we can do now is we can hit zoom square. Oh, it's making 2 revolutions. So we have to wait for it to finish its second revolution. You can see it's working up there in the upper right hand corner. As soon as it's done with that, we can hit zoom square and we can watch it graph out Jane's position with respect to time, and we can see it's a nice circle. And if we wanted to find Jane's time at exactly 22 seconds, the best way to do that would be to go to the table and start at 22 seconds and find her X and Y coordinates. But if we wanted to estimate where she was at that time, we could also hit the trace button and we can make t go up in our 1/10 of a second increments and figure out where she's at. One more option to figure out exactly where Jane is at time 22 seconds is hit second and the trace button and select value and plug in 22 seconds and it will tell you oh, I did not, my window was not big enough for that, so I need to make my window bigger. So if I go up to 25 seconds, I'm going to have to graph again, let this graph play out, and then we can figure out exactly where Jane was at after 22 seconds. So we're going to have to let this make 2 complete rotations, which will take a little bit of time. When it's done, we're going to use that value function to figure out exactly where Jane was at time 22 seconds. If you think about it, it takes 10 seconds to make 1 complete rotation. So 22 seconds, she should be somewhere between 2 complete rotations and 2 1/4 complete rotations. So second and the trace button, value, plug in 22, hit enter, and there it is. So Jane has made 2 full rotations and almost another 1/4 of a rotation. And X and Y give you her coordinates. All right, that is it for your how to use a calculator for parametric equations. If you have any questions, make sure to ask your teachers.